Hello. So it's a great pleasure for me to be to the feast of Javier. Indeed, well, when you asked me for coming to the feast of Javier, it was obvious that yes. But to come to a 60th birthday, it's always something strange, because if it is for telling that Javier is now an old man, I think that you had to make this fest a long time ago, because the first time I met Javier, it was in Dijon, in France, in 85, in April 85, if I'm not wrong. And so I was a young mathematician, just finishing my PhD. At this conference, they offered me to make a poster, like here there will be some poster session, so you will see that poster session is something important, and so please participate to the poster sessions, because, well, so I wrote some poster by hand, because at this moment we cannot make poster by computer, but okay, and there was some old and famous professor coming to me and asking about this poster, so that was Javier, because at this period, yes, it was an old man of 35 or 34 years, so very old. No, I was 24, so it was an old man. And, but now it's just my friend, so it's no more, there's no age for friends, no? And I'm just happy to make part with him, we play very nice games making ergodic theory with foliations. And is that what I will try to explain now? Okay. So that was the first thing I wanted to say before starting. The other thing is that I think that a course is for students, so I will speak for students. So it will be very elementary, and I apologize for any people which are not students, because I will say so elementary things. And for that, I will just ask, is there some student here who do not speak Spanish? Because for the real researchers, I will not, it's not important if they don't understand. I will just say is there, ¿tiene alguien aquí que no habla español? Que no entiende español? You cannot understand, and you are a student. Okay, so I continue in English. If not, I could make it in Spanish. Oh, no, I have to make the converse. Is there some... ¿Tiene un estudiante aquí que tiene dificultad en inglés? ¿O los estudiantes de aquí sí hablan inglés? ¿Todo el mundo habla inglés? Sí. Entonces, now I can continue in English. So for today, as I told you, we will mix ergodic theory with foliation. That is, we want to apply ergodic theory for foliation. And maybe, so at the title of the conference, it's about algebraic or geometric methods for holomorphic foliation. There was not at all ergodic theory inside, so maybe the students don't know what is ergodic theory. So it's application of probability to dynamical systems. So for starting this first course, I will just explain very elementary things about ergodic theory, the usual ergodic theory. So for today, I will try to explain some things about ergodic theory, which is a probabilistic approach for dynamical systems. So let's start with usual dynamical systems on compact manifolds. So we look at a compact manifold F, and I have some diffeomorphism from M to N. On dynamical systems, so we look at the orbit, that is, we follow from an initial condition, we follow by F, so we have F of X, we follow by F, we have F squared, and so on. That defines the orbits, and we want to know where are going the orbits.
write it a little bigger.
Okay, so let me go to examples. So, for examples, the simplest kind of dynamical systems are if you take from your preferred manifold M, you look at some Morse function on R. So you have some Morse function, and you take the gradient of your Morse function, and you take the time one map. So if you take F is the time one map of Morse function. Morse function. So you have your critical points of your Morse functions.
In type 1 of the gradient.
Of the gradient, yes, sorry. Thank you. Time one map of the gradient. So you have your function and you take the orthogonal vector field going down. So at each point, when you follow it once, you have that f of x will be strictly below x, except if you are at some critical point, which are fixed point for f. Now, if you follow the orbit, so it's always going down and down and down. So as you are in some compact manifold, it has to arrive somewhere. You cannot continue to just going always down. So at some moment, you arrive to some fixed point. So your orbit has to go to some fixed point, and there are finitely many of them because you look at the gradient of some Morse function, so you have finitely many critical points. Some of them are attracting points, so most of the points go to some attracting point. And if you take a nearby point, the orbit will go to the same attracting points. And there are some exceptional orbits. We are going down to the saddle to the saddle points. Other one, if you go negatively, most of the points go to a repelling point, and some specific points will go from the saddle one. Okay. So if you want now to tell to say where are going the orbits, the answer is easy. You tell, well, they are going to the attracting points. On not every point, but if you want to understand the world dynamics, you just have to tell, yes, there are specific manifolds here, which are the stable manifold of the saddle points, which are dividing the basin of your attracting points. So that corresponds to, in physics, when you have some system which is with some evolution. On when I remember when I was in at school, and we have course of physics, we make some experiment for chemical, and the teacher always say us, wait that the system go to the equilibrium. So, okay, we wait, you follow, and the system go to the equilibrium, and that was the interesting point. That, but for waiting, if you want to wait to the equilibrium of to have some chance to arrive there, you need that there exists a good notion of equilibrium. And so let me show you another dynamics, which is not exactly diffeomorphisms, but it's very easy, and for which we'll understand that it may be not this situation. Now, you look at the cycle. I take here some horizontal cycle for making the picture, and then you multiply. So take this cycle. This cycle is you go from 0 to 0, 0 is equal to 1. So here you have 0, you have 1, and 0 is equal to 1. So you have the segment 0, 1. Now you multiply by 10. So you get the segment from 0 to, I don't know the end, but at the end is 10. Now you put back here, so 1, 2, 3, 4. Well, I'm sure it's not 10, but and go back. So that is the cover of the circle by 10 leaves. So from here you have the multiply by 10, and you look at the projection. So you are in R divided by Z, which is the circle S1. On each side you look at T maps to go to 10T. Okay. And now that is my dynamical system. And so ask yourself, where are going the orbits? Well, take a number at random. Okay, so you will tell me, oh yes, 0.573. Okay, so you iterate, you have 5.71. Okay, forget the 5 because there is no 5 here. We are between 0 and 1. The next time you will have 7, 1, so you forget the 7, it remains the 1. And next time it's 0. So this point go to 0. So there are orbits going to 0. How many orbits are going to 0? Oh, easy. All what in my school was called decimal numbers. That is numbers that you have 0 points and some finitely many of them. Okay. Is there other behavior? Yes, take any rational number, then you have, if you look at its decimal, it's periodic. So you get periodic orbits. How many? Well, like rational numbers, that is countably many, but densely. In the circle, you have periodic orbits. It's a little bit wrong. It's a pre-periodic. Okay.
Yeah, because some rational numbers are decimal numbers too.
Yes. So for that, I tell now pre-periodic points. Okay. But it's also easy to see that you have points which have dense orbit. So here, if you have dense orbit, that is, if you iterate, it will go everywhere in the circle. So how now you will say, where is going that orbit? It's going everywhere in the cycle. Is that the answer that we want? Do we want something more precise? So more or less, that's the trouble. So where are going the cycle here? So the same question, but for the multiplication by 10. So that is certainly the simplest dynamics that we can call a chaotic dynamic. But as I told you, that is not a diffeomorphism. I started telling, well, I did not write it, but it was a diffeomorphism that I wanted to look at. So there are two natural ways for having exactly the same behavior, but for diffeomorphisms. The first one is look at some matrix in SL to Z. Okay, so this matrix has preserves Z square, so you can look at A as a map, a linear map from R2 to R2, preserving Z2. This allow, as it's a linear map, this allow to take the quotient of R2 by Z2, so we get the torus T2. So if you look at R2 divided by Z2, what we get is the torus T2. And now we can look at the eigendirections and eigenvalue of A. So we can assume that A has two real eigenvalues, lambda and 1 over lambda. So for example, that's happened if you take the most well-known one, which is 2, 1, 1, 1, for example. And so this one with lambda are irrational. I don't, yes. Okay. And so as there is, so lambda is, for example, less than 1. So So 1 over lambda is greater. So this implies that on the torus you have two directions, which are the eigendirections of A. One, so if you look at the eigendirections, so at each point you have these two eigendirections. These make two foliations on the torus. On one leaf, which corresponds to 1 over lambda, you have a uniform dilation by 1 over lambda. On the other, you have a contraction. So this map here is always expanding the direction and contracting that direction. Okay? Exactly, it's not difficult to see here that this map also you have a fixed point. 0 is a fixed point. If you look at the set of periodic points, it's also dense in T2. And also you have the dense orbits. Okay, so that gives us now, so as A is an SL2Z, the quotient map on R2, on the torus, is diffeomorphisms. So now we have these diffeomorphisms with this uniform dilation, like we have here by the multiplication by 10. And in fact, it's the same theory which is treating both map, which is the hyperbolic theory. And so the same question here is, where are going the orbits? And let me give you a third example, which also is very close to the multiplication by 10 or by any number. So look at on S3. So S3 is R3 on a point at infinity. So inside, I look at a solid torus. So that is here, I look at, it's a full torus. So it's D2, it's S1 times D2. S1 is a circle, this circle, and you have a family of disks, so which are the D21. And you look at a map, so you look at F, a diffeomorphisms, which send the point inside, so from S1 times D2 to itself, sending TZ on, I will just put by 2 because it's not the picture too difficult to do. So I will put 2T, and here I will put Z over 10 plus, I will certainly make a mistake, exponentielle 2 pi t de vétéran I de z pi t times 1 over 2. Okay. So let me show you, maybe I make a mistake in the formula. Let me show you what it do. So if you look at, so it's a map which projects on the circle because the image of t just depends on t, and the multiplication by 2. But if you take now a disk, what we make is a contraction by 10. So like it, we have here a disk t times d2. It will go to 2t times d2. But we first make a contraction by 10, and then we make a translation so that it will be on the circle of radius 1 over 2, center on that cycle. So it's a small disk there of radius 1 over 10. And this circle is running when t is going there. This circle will make one turn. So that what we obtain like that is that the solid torus is sent inside itself like this. So you see, that is once more a solid torus, but which turn twice inside my initial solid torus. So this is a diffeomorphism from the solid torus in its image, which is inside itself. It's not difficult to see that if you look at the complement, so this is, it looks like something which is knotted, but it's a trivial knot. So the complement, it's still the complement, isotopic to the complement of the solid torus. So you can complete this map on the wall S3. So you get on S3 diffeomorphisms which have some solid torus on which we have this behavior. So the orbits are going inside the solid torus, and if you iterate, you will get that this solid torus will go twice inside this one that is 4 times inside the big one, and so on. So you see that this dynamic is very close to be the multiplication by 2, so it will present exactly the same difficulties as the multiplication by 2, which is the same as the multiplication by 10. So in some sense, I present you 3 rich dynamics, but these rich dynamics are the ones that we understood well, because there are many chaotic dynamics that we do not understand so well for the moment, but these ones are what are called the hyperbolic dynamics, and for them we have a pretty good theory. So now that, for example, for the multiplication part 10, telling where are going the orbits, it looks difficult to give a general answer. Well, there is some crazy idea that let's try with the probability to see if the probability will give you a better answer. So let me now speak on probabilities, and then I will go back to dynamical systems. And for the next course, the next courses, I will pass to foliations. I think, okay. So for the moment, just recall the minimum that we want to know about probability. So I have my compact manifold. And I look at probabilities on M, the set of probability of M. So what is the probability of M? So M is a metric space. So I have notion of continuous maps, and I have the notion of Borel sets. So if I take some set, some open set or some Borel set, I want to tell what is its mass. And it's a probability, so a probability is something which tells to every open or closed or more generally Borel set what is its mass. And it has to be positive. And the total mass, that is the mass of the manifold, has to be 1. So I have mu, so that if you have X inside M, you have a Borel set. Then mu of X will be between 0 and 1. And mu of M is 1. On the other hand, you have the continuous function on your manifold. So a measure is something that if you have phi from M to R continuous, so you can integrate phi by this measure, so it will belong to R. And if phi is positive, then the integral of phi will be positive. And the integral of 1 is 1. So, okay? This set of probabilities has many natural topology, but I will always use the same topology, which is called the weak topology. On P of M, which is that we say that a sequence of probabilities tends to a probability if for any continuous function we have that the integral of phi for my probabilities tends to the integral for mu. Okay, so that is the weak topology. Using that, the space of continuous function on M admit a countable dense subset. It's easy to see to get a distance. So that is a metric space for this topology. So that is P of M is a metric space. And what really interests me is that, so now I put the first theorem, first classical theorem, and that is P of M is a compact metric space. Okay, so we started with some compact manifold, and we get a compact metric space of the probabilities on my manifold. There is other things that interest me. So the integral is something which is linear. So that makes that my set of probabilities is naturally included in some vectorial space. On inside, it convex, because if I take two probabilities, and if I make a convex barycenter between these two probabilities, it's easy to see that it's still a probability. So P of M is also convex. Okay. So I think that, oh no, okay. I think it's just what I wanted to say. Okay. Now, we want to relate that to the dynamics. So for that, we will look at, so we assume we have our diffeomorphism f of m. Now, we will look at invariant probabilities. So now we have a dynamical system, f from m to m, a diffeomorphism. So we will say that mu, a probability, is invariant if for any Borel set X, you have that mu of X is equal to mu of f of X. And it's not difficult to see that is equivalent to say that for any map phi from M to M, from M to R, sorry, continuous map, we have that the integral of phi is the integral of phi times f So in fact, when you have any map, you can always, if you have some application from M to M or from M to another manifold, you can push forward any probability by F by exactly this formula. But if you have this formula, So let me just give examples. Clearly, if you have X is a fixed point, then the Dirac measure at X, that is the map which at any continuous function is the evaluation at X. So the Dirac measure is invariant. But now if you have a periodic point, if you have X which is periodic, that is, you have Fn of X is equal to X, then you can look at the Dirac at all the points of the iterates of X. Now you can make the sum of all these points in the orbit, so from 0 to n minus 1. So that is invariant because F induces a permutation from the Dirac at Fi to the Dirac at Fi plus 1, but it's not a probability, so you have to divide by the period for getting a probability. So let me give you other examples. For example, if you look at, so here I put for diffeomorphisms, but if I look at for not invertible maps, that is not a good definition. Because if you look at some set X, and you look at its characteristic function on X, so if you look at this, is the characteristic function on f minus 1 of X. So in fact, for non-invertible maps, it's much better to put here minus 1, which for diffeomorphism, it gives the same. So look at now the multiplication by 10. So for the multiplication by 10, then you have Lebesgue measure is invariant. dt is invariant. Why is that? Because if you take any set in 0, 1, and if you want to, you look at its mass, take the preimages. You have 10 preimages which are disjoint, and each of them has been contracted by 10. So you recover the same mass. So Lebesgue is invariant. Okay? Or for example, for the anosoph, which you can already see there, as it starts with a matrix in SL2Z, the determinant is 1. So if you look at for the anosoph map A from T2 to T2, so as the determinant is 1, so the Jacobian of the map at each point is 1, once more, Lebesgue is invariant. So now the objects will be invariant probabilities. I show that there are examples of invariant probabilities, but why do you is there always invariant probabilities? Entonces, so F, once more, is from M to M, and M is compact. Take any point X and look at exactly the same formula that I put here. So you look at the Dirac measure at the iterate of X. You take the sum from 0 to n minus 1, and you divide by n. Okay, so let's show the picture. So you have x like that, and you have its orbit. So f minus 1 of x here, f of x here. And I choose n of this point. Okay, and I take the natural probability here, which is taking the Dirac at this point, and to take the average by the number of points. So that gives you a probability. So that is mu xn, and this one. What happens if I apply f to that? Well, the probability at this point will give you the probability of that point. From this point, we'll go to that one. So it's the same that for periodic points, you have a permutation of that point. But there is this one, which is going outside to fn plus 1. And for the image, this one disappears. So this probability is not invariant. But what is the defect of invariance? The defect of invariance is this point on this one, but divided by n. So the total mass of the non-invariance is 2 over n. So now assume that you make n tends to infinity. So, okay, it's not an invariant probability, but almost. Because really there is a small mass which is going away, but the rest remain invariant. And now you remember that the space of probability is compact, and you can take a subsequence of that. So there exists ni, such that mu of x ni tends to mu. And for each of them, the defect of invariance is 2 over ni, and ni tend to infinity. So for this one, the defect is 0. That is, we get an invariant probability. So mu is invariant. In fact, here I started with a point, and I took the simplest probability, which is the Dirac one, but you can make the same trick using any probability. You take a probability, you make the average of the iterate of it along a segment of n iterates. You take a sequence of that converging to something. This something is invariant. So we have, a priori, plenty of invariant probabilities. Okay? There are, besides invariant probabilities, there are some of them which are more beautiful, and they are called ergodic probability. So, as I told you, the space of probability is convex. So now we can make bicenter between probabilities. But reversely, if you have a probability, is it the bicenter of other one? So for example, you assume that you have an invariant probability, an F invariant probability. And now consider X an invariant set, subset M an invariant set, an invariant Borel set. So I assume that f of x is equal to x. And I will assume that mu of x is strictly positive, but also strictly less than 1. So if you look at the complement, it's also invariant and has the same at a non-zero mass too. So now you can look at mu and you restrict it to X. That is, if you take any continuous map, if you want to integrate it for this measure, you multiply by the characteristic function of X, and you make the integral of the product. Okay, that is a positive measure, but it's no more a probability because the total mass is the mass of X. So for getting a new probability, I divided by mu of X. So that is a new probability. So that I could do with any X, but as X is invariant, that is in fact an invariant probability. So let me call that mu X. So in the same way, I have mu Y, and it's more or less easy to check that mu was equal to mu X, mu of X, mu X, plus mu of Y, mu Y. So you can decompose mu in a barycenter between two other invariant probabilities. Okay. So when you cannot do that, it means, so when you have a convex set, you have the extremal point of the convex set, and that precisely the point you cannot decompose in barycenter. But you see, it's precisely the probability which do not admit any invariant sets excepted the one with total mass. So the definition is that mu is Ergodic if for any X Borel set, if you have that f of X is equal to X, this implies that mu of X is 0 or mu of X is 1. And that is equivalent to mu is an extremal point of the convex set P of MF, the set of invariant probability. Okay. So let me make show some examples. So I did not give you many examples of invariant measures. So so it's more or less clear that this one is ergodic. I guess that this one it's an exercise to check that it is ergodic. Here, the definition for not invertible map is the same. That is, you don't have any invariant set except if the mass is 0 and 1. So let me check that Lebesgue is ergodic. How you do that? Well, take some set with positive Lebesgue mass, which is invariant by the multiplication by 10. And now you have to remember your courses of about measures, about Lebesgue measure. So if you have some set with positive Lebesgue measure, it has density points. What is density points? So you have X, let me make a picture. So you have some set is Lebesgue of x non-zero. Then you can look at small intervals, En. So now look at this interval, En, and you look at how many points you have there, and you see that x is almost all. That is that Lebesgue of the intersection with this interval divided by the length of the interval is, for instance, larger than 1 over n. So you have, for any n, you can find an interval where your set is almost filling the whole interval. Okay, but it's a very, very small interval.
Larger than 1 minus, larger than 1 minus.
Better, yes? But it's a very, very small interval. It's an interval of length something, but this is a very, very small place. But you multiply by 10. On 10, you certainly preserves the proportion inside the interval. So when you multiply by 10, you have such an interval, but of length 10, 1, the initial one, having exactly the same proportion. And you continue iterating. As your set is invariant, you get an interval, a large interval, with a proportion which is larger than 1 minus 1 over n. So now you get, in fact, by multiplication, invariance by multiplication by 10, so you can choose, you can assume that the length of yn is between 1 over 10 and 1. Okay? Now, such an interval have a big overlap. If you take a sequence of that, you can always extract subsequences tending to some specific interval. So you can assume also that E and I tend to some specific I. And inside this I, what is the proportion of x? Well, it's larger than 1 minus 1 over n for any n. So it's 1. So now we have an interval which has full measure of points inside x. You iterate it once more, it covers the whole circle. So you get that in the whole circle, the total proportion is 1. So you get that finally the mass of x was 1. Okay, so we get that this was ergodic. Let me show you now that this one is ergodic too. So that is some argument which is called, that I will not do. I think I will not do today. I have to explain something before, on something not so short. Oh, that's okay, so we have seen examples, and now are there always ergodic measures? And the answer is yes. So theorem. So we have seen that there are always invariant measures, but so I have f from m to m, and I'm using that m is compact. So if you have mu an invariant probability, then there exists a unique probability measure on the set of ergodic measures. of f, such that mu, so let me take that in terms of continuous function. If you take a continuous function from M to R, then the integral of phi for mu will be the integral along the for d theta of the integral of phi for nu ergodic. That is, any probability, you can disintegrate it in a convex sum, so in integral, on ergodic measures. And furthermore, this is unique. So let me now, so we introduce probability, invariant probability, and I said that there was more beautiful probability which are ergodic. But
Do you know a good reference for that theorem?
Choqué.
No.
Choqué will take the existence. So, in fact, in that theorem, there is one part which is the existence, and it's not very difficult. And for the uniqueness, I will need Birkhoff's theorem. So, because there is some meaning of this decomposition. Because I put the problematic here, I'm sure that the problematic is that uniqueness, because if you have some convex space, I think that you can decompose that point in several ways as barycenters of extremal points. So the uniqueness is not at all given just by convex theory.
But Marcelo Viena in his page has a wonderful little note on Rockling's decomposition theorem. He gives a proof, and that's a cool.
So you say that, what's the reference?
Marcelo Viana's homepage.
The notes on the Rockling decomposition theorem. So he proves a larger theorem and gets this. That's a beautiful application. And it's really clear.
So in fact, I can explain the proof, but I'm very bad for references. Sorry. So let me come back to the dynamics. What are the consequences for dynamics, for describing the orbits of the existence of invariant probabilities? So first, I think, well, I'm not sure, but I'm not good also for historical stuff, but I think that the idea of using probabilities for dynamical systems comes back from Poincaré, if I'm not wrong. And so let me recall the Poincaré recurrence theorem. So I have always my compact manifold on F from M to M. Diffeomorphism. Here it could be an homomorphism, and you can also make in a much more general setting, but we deal with diffeomorphisms here. And you have mu, an invariant probability. So, yes, the F. And you assume that you have some set with positive measure. So there exists a subset x0 of x with the same measure. such that if you take x in x0, you have a positive number, and there exists negative number 2. Oh, okay, I will put both positive, such that fn of x still belongs to x0, and f minus m of x still belongs to x0. That is, we have a subset of full measure, such that if you take any point, it will have a return point inside. And so you can continue, you can iterate that. So you get a new dynamical system looking at, so you have the Poincaré map inside x0, p from x0, from x0 to x0, the first return. And that will preserve the restriction. Preserves mu, what I called mu x0, that is mu of x0 multiplied by mu restricted to x0. So we get now a new dynamical systems preserving the normalized measure mu restricted to x0. As I'm arriving to the end of my talk, and I would like to enunciate Birkhoff's theorem, I will not give the complete proof of that. But the idea is easy. You first start with x, and you look at the point which have no return inside x. And you assume that there is some mass in the point which have no return inside x. But if you have no return inside x, so you assume that you have y included in x with mu of y positive, and if you have x in y, then for any n positive, fn of x never come back in x. Now you look at to x. Now you look at f of y. F of y is outside, so in particular is disjoint from y. So now if you look at fn of y, it's always outside, donc it's disjoint from y. But if it's disjoint from y, you deduce by iteration that is disjoint from any of the previous iterates. So you have that all the iterates are disjoint. And you have an invariant measure, and the measure of y is positive. So now you have y, f of y, and so on, fn of y, and so on, which are disjoint sets with the same measure. But the total mass is 1. So the sum of all that has to be less than 1, but you take n times the constant is less than 1 for arbitrarily large n, so the constant is 0. So the hypothesis here was wrong. So this gives you immediately that almost every point in x have a return in x. Now, the one which I pretend that you have a return inside. So now you can look at the one having just one return but not two return, and you will make the same argument. You will see that the mass is 0. So finally you get that almost every point have infinitely many return, and where they come back, certainly they go back to the point with infinitely many return. So you get that, in fact, the set you consider is invariant. So you get, okay. Let me just now state what is certainly the true starting point of ergodic theory, which is the Birkhoff theorem. So I will just state it in my setting of diffeomorphism manifold, but it's true in a much larger setting. So Birkhoff ergodic theorem. So M is my compact manifold, and I have F from M to M. It can be an homomorphism or diffeomorphisms. So you have an invariant probability. T. So there exists some subset X with total mass such that if you take X in that set, and you take any continuous map then if you look at the average of this continuous map along that orbit, along the positive orbit, that is, you make the evaluation of f of phi on fi of x, and you take that from 0 to n minus 1, and as you want an average, you take, so the zero sum, you divide by n. So this will converge with the limit exists. The limit exists and is equal to the same limit when you take the iterates going to infinity. So of the same. So minus e of x from 0 to n minus 1 over n. Okay? Furthermore, so let's call that I will call that big phi of x. So the theorem tells that these limits exist and are equal. And furthermore, if you take now the integral of big phi of x is the same as the initial integral. Okay. So for the moment, Birkhoff theorem tells us that if I take an orbit and I make an evaluation of a continuous function on it, you see a good average of your function. And the miracle when your measure is ergodic is that, in that case, phi of x does not depend on x. So the phi of f is equal to the integral of phi along mu. So that is, if you want to make the average along the time of your function phi, in fact, you make a space average of your function phi by your measure. Okay? I think I'm over time, so I have to stop. May I have 3 minutes more? Okay. Just because next time I want to speak on foliation, on no more, on forget, well, no, I don't need, because I want to make that the Lebesgue measure for the Anosov map was ergodic, so I will come back to the usual ergodic theory. I think it's better to stop here, not making.
Thank you very much.
Las preguntas pueden ser en español, eso ya bueno que los alumnos las veces me interrumpo si yo no estoy claro cuando hago mis explicaciones, ¿no? Mis explicaciones. Entonces, por favor, yo quiero animar a los alumnos a hacer todas las preguntas que gusten. Y puede también hacer des preguntas personales después. Okay.
Muchísimas gracias.